Hello everyone, I am Sinyan Lee, a doctoral candidate from the Korea University. Today I will be presenting my research title, Numerical Analysis of Gravity Connection and No-Pressure Wind Turbine under Ultimate Load. The contents of my presentation is follows. Offshore wind turbine comprise a turbine and a substructure, and the part that connects them is known as a grout connection. The grout connection serves as a structural element to withstand lateral wave and wind loads. A reinforcement shape called the shear key has been suggested to elevate the shear force. Let me explain the stress transmission mechanism of shear key. The shape of shear key can be idealized based on its support condition. The load transmitted from the top from strut as it going down and across to the opposing node. However, controlling the seabed condition is challenging when the construction error occurs. The position of the shear key changes, which in turn alters the stress distribution. This can consequently lead to reduction in the ultimate load capacity. To design the shape of the experimental model, we refer to the DMV guidelines. The formula are presented based on the diameter, thickness, and the ratio determined by shape of the shear key. The design value within certain range are suggested, as shown in table below, and the design was conducted according to these guidelines. The specification of the experimental model are as shown in the provided drawing with a height of 900 mm. There are a total of 3 test specimens differentiated based on construction errors of the shear key. For the numerical analysis, we utilized the Abacus software, employed the concrete damage plasticity module. The mesh size was set at 2 mm, and to ensure computational results, a 2D axial symmetry type mesh was used. I will briefly explain the procedure for creating the test specimen. We employ the CNC process as shown, and the grout utilized as a strength of the 80 megapascal, while the steel has a strength of 355 megapascal. Next, let's move on the setup of the test specimen. LVDT were installed both above and below to measure relative displacement. And a 500-ton actuator was employed secured to the base plate. Looking at force displacement curve, we can observe the yield load for each test specimen. In the nonlinear range, the degradation of the grout accelerates. Furthermore, the yield loads were measured as follows. In comparison to easier model, the E50 model experienced a decrease of 18.31% in root, while the E100 model exhibits a significant reduction of 53.80%. Let's examine the crack patterns for each test specimen. For E0 and E50, it occurs local occurring, and the pipe does not slip over, injuring support performance at the grout connection. On the other hand, the E100 model does not experience local buckling. It because the maximum load was 53% compared to E0, and it could not support a load that would cause deformation. And also slip displacement of inner pipe was measured through the LVDT. We compare the numerical analysis results, the crack patterns for the easier model. Pictures occur on both opposite hierarchy and diagonally. The E100 model demonstrates the straight angle of 23 degrees, as excessive load transmission downward led to this result. Notably, stress concentration occurred at the outermost bottom, indicating separation of the grout layer due to occurrence of failure in the test specimen. The observed crack can be explained as this failure mechanism in the E100. And the next, here are the relative displacement results. At 3,000 kilonewton, the inner displacement of E100 was 4.6 millimeter, which is more than 3 times the displacement of E0. E0 had the least inner displacement compared to other models, while its outer displacement was the most significant. Values measure decrease proportionally with length from the top, with the largest value at the top and smaller values further down. However, at the location of pipe 2, deformation similar to buckling was observed, resulting in values similar to larger measurement of pipe 1. Shear stress is transferred from the inner steel pipe, with the deformation rate of the lower section 7 being the largest measured. For the E100 model, no linear behavior was not well measured by the strain gauge. This seemed to be because the destruction energy is not transferred to the steel, but transferred to the grout. This study analyzed the actual load capacity according to construction error in the arrangement of circuits when using 80 megapascal grade grout of the downside offshore wind turbine grout connection. For the model, where the construction error of circuit was 50%, the actual load capacity decreased 18.31%. For the model with 100% construction error, there was a 53.80% reduction. In the model where the maximum construction error of the circuit occurred, crack formation in the circuit was observed in the vertical direction. This prompts additional destruction in the grout, leading to decrease in load resistance performance. Although this study evaluates only under actual load condition, it seems that the degradation in structural performance will be further exacerbated when lateral loads and moments act simultaneously. Well, this brings me to the end of my presentation. If you have any questions, I'd be pleased to answer them. Thank you.